We share
facts within the scope of applied mathematics.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others. Please subscribe to our channel if you like our videos.
Hello everyone, you are welcome to the last part of MTS 104, that is third lecture. So in this video I will continue from where I stopped. Like I've said earlier that this last part is more than 10 pages, so this one is 17 pages, you can see from here now. So let's start the journey. So let's continue from 50 points now. We are familiar with the equation of motion, and there are three of them, and I've shown you how to use the concept of calculus to obtain these three equations. That should be in our fourth lecture. So these are the three equations of motion, and here is the final velocity, initial velocity, and then the acceleration multiplied by the time. And this one here, we call this one the displacement, and at the same time we have is equal to initial times the temperature, initial velocity times time, and then the average of the square of time multiplied by acceleration. So we have the third one. But do you remember that the three of them have acceleration due to gravity? And do you remember what I told you, that in this case acceleration is a constant property. It is constant, it is fixed. It is 9.81 meters per second square. Please take note of that. That is very important about these three questions. So let's go to number 6 now. It's a case of an object being thrown upward. Now you see now that by the time the object is thrown up, now one thing is that in this case the acceleration is minus gravity. That is minus g. So for the upward motion, we have the gravity to be minus because the object is moving against the acceleration. So in that case, the acceleration for this motion from here to here is minus. And when it gets here, you know that the velocity is actually 0. And when the velocity is 0, then at this point now, for this one here, the final velocity is 0. And for the one that is coming here, initial velocity is what? Is 0. That is why you see u is 0, v is 0 at the highest point. Because for this case now, for the object, for the upward motion, we have the final velocity, are we together now, to be 0. And for this case now, for the one that is coming here now, we have for the initial velocity to be 0. Now let's consider example 1. A barrel is thrown vertically upward. Don't forget, looking at that word, vertically upward, it means that the acceleration is minus g, with an initial velocity of 60 meters per second. Now we asked to find the velocity after 4 seconds that the object has been thrown up. And even what will be the maximum height that the object will reach. And the third question is that we should calculate the time taken for the object to reach the maximum height. And number D, we should get the time taken for the barrel to reach the height from the ground. Now let's solve the problem now. In this case, the object was thrown upward at the initial velocity of 60 meters per second. So that means that u is 60 meters per second, and here acceleration is minus g. Why is it minus? Because the object is going upward. And what is the time? The time is 4 seconds, because we learned that we need to know the velocity 4 seconds. That means that the object from here, 1 second, 2 seconds, 3 seconds, 4 seconds. Then at 4 seconds here, we want to know the velocity. So in that case, we have the. So let's consider the first equation of motion according to Isaac Newton, which says that B, final velocity, is what? Is initial plus acceleration times time. So in this case, since acceleration is minus g, so we have this. So this one will give me 60 meters per second minus g here is 10 meters per second squared. Then time is 4 seconds. See, seconds here, you know, is plus 1. Plus 1 and minus 2 will give me minus 1. So that is why the combination of gravity and time will give me the same unit with velocity. That is it. That is what it means. So I have 60, which is initial minus 40, and that will give me 20 meters per second. Which means that after 4 seconds that the object has been thrown up, the velocity is 20 meters per second. Now, the second question is that we have to calculate the maximum height that the object will reach. Don't forget that as the object is going up gradually, the maximum height is attainable when the final velocity v is 0. Take note of that. So let's solve this problem now. The maximum height attained, let the maximum height be in h meter. Also, at maximum height, final velocity is what is 0. So let's use the equation, which is v squared is equals to what? U squared is plus 2ax. So for this now, we have u to be u squared, then we have a to be minus g, then we have 2. Then here, the displacement here is what is height. You agree with me? It's height. It's height. Displacement here is the same thing as what? It's the height, because the object is going vertically upward. Now you now see now that this the equation is very good for object that is moving horizontal, and it's also for object that is moving vertically. So in this case now, we have this to be minus g, because acceleration is what is minus g, because the object is moving upward. So the final velocity is what is 0 squared. Then we have 60 squared minus 2 times 10 times h. So if you find 0 squared, this one will give me 3,600 to go to the other side. So what about this one? 2 times 10 give me 20. So by the time this one come, it become minus. The minus will cancel this minus. That means minus 60 squared minus this one. The minus will cancel. Then you now have 60 squared divided by 2 times 10. That is 20. So we cancel. Then the height is 180 meters. So we that if the object is thrown upward, and we know the velocity, the starting velocity is 60 meters per second, it means that at exactly 180 meters, the object will stop and it will start coming down again. That is what it means. Now let's go to the third question. What is the time taken to reach the maximum height? Okay. Now in this case, now we want to know the time that you take the object. Don't forget that we only calculated what the velocity will be at exactly 4 seconds. So this time around now, we need to move forward to get what will be the maximum, the time taken for this object to cover 180 meters. So what do? We know the initial to be 60, then g is minus then times t. So in that case, it will be the maximum is when v is 0. Don't forget that the maximum height, the velocity is what? The final velocity is what is 0. So from here we can see the standard formula, then we have to be 6 seconds. So which means that after 4 seconds, after 4 seconds, after 4 seconds, the velocity is actually 20 meters per second. Then the maximum height is 180. Then it means that at exactly 6 seconds, the object will reach the maximum height. Now, what is the time taken for the barrel to reach the height from the ground is the same as the time taken to return from the height to the ground. What am I trying to say is that if from here to here is 6 seconds, then from here back to this point we also go 6 seconds. What I'm trying to say here is that the time taken for the object to move from here to here is 6 seconds. Then from here to here is what? Is 6 seconds. Please take note of that. This diagram is not that really perfect to explain that the object is moving. But what the question is saying is that the time taken from here to here and here to here, they are the same. And that's why I have 6 plus 6 seconds. So the time taken for the barrel to reach the height from the ground. So let's proceed now. The second question we're going to solve now is that a stone is thrown vertically upwards with an initial velocity of u meters per second. It reaches a maximum height and returns to the ground. It reaches a maximum height and returns to the ground. Find an expression for A, the maximum height, 2, the velocity on hitting the ground. Find an expression for 1. We need to find an expression for the maximum height, and we need to find an expression for the velocity on hitting the ground. So solution at maximum height, v equals to 0, and here we have v squared equals to u squared plus 2ax. So we have u squared, then acceleration is what? It's minus g, so minus 2 times h. So substitute v equals to 0, then 0 equals to what? U squared minus 2gh. So from here we can make our height to be u squared over 2g. So the second part now is that we're asked to find the velocity on hitting the ground, and the velocity will be the final velocity, that is v, and unit is meter per second. So here we have v squared is equals to u squared plus 2gh. So here acceleration is equals to what? Plus g. Then when the stone is coming down, don't forget, when the stone is going up, it is negative. When the acceleration is negative, but when it's coming down, the acceleration is positive. When the stone is coming down, then v squared is equals to u squared plus 2gh. Then v squared is equals to what? Then 0 plus 2gh. Then we have v is equals to square root of 2gh. So let's take a look at this tutorial question, which is similar to the first one that I've solved. and that is within page 43. So the tutorial question is this: a ball is thrown vertically upward with an initial velocity of 10 meters per second. We're asked to find the velocity after 6 seconds. We can find the maximum height attained, the time taken to reach the maximum height, the total time taken for the ball to return to the ground again. In this case, neglect air resistance. Even don't forget that we've talked about this in our first part. That is the contribution of the pioneer of motion dynamics. So don't forget that most times we throw two objects upward, then the air resistance can be assumed to be negligible because both of them will go up, they'll come back, provided the object has a significant mass. So now let's take a look at this tutorial question again. When an object is thrown up, it experiences dash due to the dash of the earth, which tends to pull the object downward. Now, if you look at this question now, you see now that when an object is thrown up, it experiences something. What is that thing? Can you guess? Can you try? Okay, you can drop the answer at the comment section. But what exactly will make the object to come down again? There's another thing again. So we have the first option to be momentum and acceleration. We have acceleration and momentum. We have retardation and gravitational. We have gravitation and retardation. So pick the correct answer. So let's go to the third question. Which of the following describe the acceleration due to gravity? When an object is thrown upwards, it rises to a particular height, and then what will happen? It moves forward in the air. Is that really possible? It moves backward in the air. Is that possible? It continues to move upward. Then it falls back to the ground. It falls back to the ground. Now let's go to the fourth question. If a body is dropped from a height 20 meters, the initial velocity is dash. Now look at that question. If a body is dropped from the height of 20 meters, look at it now. What will be the initial velocity? The answer is very simple. I've said it earlier. Take your time to read through, then to pick the correct answer. So that is all with that. Then let's go to page 44. Here now, we want to talk about the laws of motion under gravity. So this is exactly where I explained that I will discuss a lot of things concerning the first law, second law, and third law of motion. So let's take a look at it. So it's just a kind of interesting story. So we all know that an object at rest will remain at rest if left alone, and that an object in motion tends to slow down and stop unless some effort is made to keep it moving. This is very simple. Let's consider a ball. I'm holding a ball and I throw that ball. You will notice that the object, the ball, will continue moving, except one. There's this force tend to stop the ball moving, to stop rolling. That is what this law is talking about, that the object will remain to be at rest. That is, if I should put the ball on the ground, I didn't touch it, the ball will be there forever and ever, except there's someone that acts on it. And even if the object is moving, except there's a force tends to stop it. Those are the two things there. Now let's consider the following questions. What happens to an object when there is no net force exerted on it? What will happen to that object? Now, what's linked force to acceleration? I want to get it now. But if you look at the first question, it's very familiar. I think we've answered this question before. Because the question is this: what will happen to an object when there is no net force exerted on it? When there's no force exerted on it, what will happen? Definitely the ball will eventually come to rest. Is that what you're saying? Okay? Because we know that provided, according to inertia, what the law is saying is that the object will continue moving. And if there's a force on it, the object will continue going on, will continue moving. But when there's a force, the object will stop. This is actually what we want to discuss explicitly. So what links force and acceleration? What happens to an object that exerts a force on another object? What happens to an object that exerts a force on another object? Now, answers are contained in Newton's 3 laws of motion. So let's consider number 1 now. When the vector sum of force on an object is 0, what I'm saying here is that all the summation of forces on that object, for the object to be moving, there are 4 forces. Are we together? The one that is going forward, the one that is going up, the one that is going down, and the one that is trying to push the object backward. So in that case, if an object is moving straight on the ball, like a case of ball is moving on the surface, there are 4 forces. So what I'm not trying to say is that if we sum all the forces together and the summation of all the forces is 0, then the acceleration of that object is actually what is 0. Now, from here, you now see that I've mentioned 2 points now. I've mentioned forces, I've mentioned acceleration. So, but one thing is that if the forces is 0, then the acceleration will also be 0. Now, what does it mean from here? It means that force must be applied to an object to change its velocity. Without force, the velocity will be the same. That is why you notice that in this part, in this course, there are some cases whereby we don't even talk about the force, because we believe that the force is the same, it's constant. Take note of that. So that is what it means that force must be applied to an object to change its velocity. So in the case that there is no force, it means that the velocity is constant. Now, when the vector sum of forces is not 0, in this case now, the summation of all the forces acting on the body, if it's not 0, then what does that mean? It means that force is related to acceleration. Let's take a look at this sentence again. When the vector sum of forces is not 0, it's not 0, it means that the force is actually the same, is something. Maybe 1 Newton, 2 Newton, or 3 Newton. So in that case, the force is related to acceleration. Now let's go to number 3 now. This one is the first law of motion. This is the second law of motion. This is the third law. Now, this one is saying that pure forces that interacting objects exert on each other, as in if we push an object, it pushes back with an equal force, but in the opposite direction. Which means that if I should open a door now, let's for instance now, a particular object, if I should exert a force on it, then definitely there will be a kind of counter force, which is of the same magnitude but of different direction. So of opposite direction. So let's now go detailed now to the Newton's law of motion, the first one. A body at rest remains at rest, or if it is motion, it remains in motion at a constant velocity. When can we have a constant velocity? Now let me ask you that question. When do you think we can have a constant velocity? We can have a constant velocity when the force is also constant. So when the force is constant, then definitely we have a constant velocity. So here now, the object will remain at rest, or if in motion, it will remain in motion at a constant velocity unless acted on by a net external force, unless there is an external force on it. In that case, then the velocity will change. And if the velocity change, then it means that if the velocity is negative, are you together now? Then the object will stop, or there will be a kind of retardation. And if the velocity is increased, then it means that there will be a kind of acceleration, then the object will keep on moving. So there must be a cause. What I'm trying to say is that for the objects to experience this law, there must be a cause, which is a net external force. It's a net external force. Now, the second thing we need to note is that for there to be any change in velocity, either a change in magnitude or direction. Now, what can make I think I've explained this. What can make the velocity change? The velocity may increase or decrease. So, if velocity will increase, then it means that there will be a kind of acceleration. If the velocity will decrease, it means that there will be a deceleration. So, in that case, there are two things now that we need to know about Newton's first law of motion, which is that there will be a net external force. And the net external force is actually constant. Are we together? Because that is why we can have a constant velocity. So, and at the same time, there must be a change in magnitude or direction, because we are dealing with velocity, and velocity is a vector. So now let's consider this counterintuitive of first law of motion. This thing is very common. You see it in most textbooks. They call it counterintuitive of first law. Now, do you know that if you look at the first law very well, with a body at rest remain at rest, or if in motion, remain in motion at a constant velocity unless acted on by net external force. Do you know that what this thing is saying is that once an object is set in motion with uniform velocity, no force is needed to keep it moving. This interpretation seems contrary to everyday experiences. That is true, because if you look at it very well, you see that once an object is set in motion with a uniform velocity, no force is needed to keep it moving. Is that true? That is what we call counterintuitive of first law of motion, because that is what the law is trying to say. That is that really what he's saying? Now, let's go to the second part now. And now, to explain this now, I will now bring some facts to really explain. Now, let's consider this. An object that is sliding across a table. Oh, before I proceed to this counterintuitive, there is something connected to this. And that is what we need to bring out now. And it has to do with frictional force. You know, we are talking about net force. So frictional force is also part of it. So let's consider an object sliding across a table or floor slows down due to the net force or friction acting on the object. Now, let's take a look at this again now. We have a surface now, and we have an object that is sliding across it or floor slows down due to the... So if the object is actually trying to slow down, then what will make the object to keep on slow? What will make it? The answer is very simple. It's because of friction. Because if you look at this now, you know what we are saying, that once an object is set in motion with uniform velocity, no force is needed to keep it moving. But what about if there is friction? So friction is a force. That is it. Friction is a force. So let's consider this example one now. We have a surface now. Then the object is moving on the surface. Then friction will set in. And friction is also a force which will eventually make the object to come to rest. Let's take a look at that one. Likewise, if you push a book across a table, the book does not keep moving indefinitely after it has left your hand. It slows down. Now you have a book on the table, and then now you exert a force on it now and you let it go. You notice that there's no way now the book will eventually slow and stop. Why? Because of friction. Let's consider that example. Consider again what happened to an object sliding along a rough horizontal surface. If the surface is rough, note that one, the object quickly grinds to a halt. It means that the object will quickly stop because the surface is rough. And when the surface is rough, then the friction is very high. If we spray the surface with talcum powder in order to make the surface smoother, then the object slides faster. You know, in this case now, let's say, you know, there's a machine that the people in the furniture, they normally use, carpenters, they use to clean the surface, to make the surface to be shiny, to be smooth. So if we should use powder to make the surface to be smooth, to be even more smoother than before, you know that the object will cover a larger distance compared to the first one that is very rough. Now, if we make the surface even smoother by rubbing lubricating oil on it, the object slides further. So you now see that in this case now, the friction is very high, the friction is medium, then the friction is very, very low in this case. Now let's go to the next one again. If the surface is frictionless, then the object will slide in a straight line indefinitely. If the surface is frictionless, then the object will slide in a straight line indefinitely. If the surface is frictionless, it means that there's no friction at all. If the surface is frictionless, there's no friction, then the object will slide in a straight line indefinitely. There is no distinction between an object at rest and an object moving with a constant velocity. Look at it, there is no distinction between an object at rest. In this case, object at rest, the velocity is 0. And then the object that is moving too. Again, since the object is at a constant velocity, then it means that the force is the same. How to get that now? Okay, that means that there is no net force. So in those two cases, now you say that there is no net force. If it's in this case now, V is 0. There's no force acting on it. That's why the velocity is actually there. And in this case, if there's a force on it, now you together. So that's a constant velocity. So constant velocity means constant magnitude and constant direction. Now you can ask now that based on this, now we've talked about friction as a major factor that can affect Newton's law of motion. Because in real life, friction is there. Even if you put on a slippers, you notice that the major function of your shoe is to help you to handle friction. That is it. That's why if you see a newborn baby, a baby that is just trying to walk, you see now that they find it difficult to really position themselves to resist friction. So let's proceed now. So what is not friction now? Friction is not the cause of the slowing. Friction is something that can make any object that is moving to slow down. Frictional force slowing the motion down, the object will not slow down at all if friction were completely eliminated. I'm saying that if there's no motion, if there's no friction, and the surface is very smooth, That means that the surface is very, 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 very smooth. Then the object will keep on moving. Now, if we know enough about friction, then we can accurately predict how quickly an object will slow down. That is, if we know a lot of things about friction, then we can determine when the object will come. So let's take a look at friction again. It's a force that opposes the motion past each other of objects that are touching. Friction is an external force. Friction works against forces. Friction opposes direction. So if the object is going forward, friction will be going backward. And then they're not dependent on speed. Even friction is not dependent on the area of the contact. It is only dependent on weight. Now, look at this point I'm bringing out to you now, that friction is only dependent on weight. Now, if a man of 50 kilograms and a boy of 5 kilograms are walking on the same surface, you will notice that the man with 50 kg will experience a friction that is quite different from a boy of 5 kg. Why? What means? It means that the weight of the boy of 5 kg is very small. So the friction that will be there will be very, very lower compared to a boy of 50 kilograms of weight. So you cannot see that here that friction is dependent on weight. So please take note of this question, which I've explained that friction is dependent on weight. And even another reason is because that is why, let me explain this to you. You will see a car, they will make sure that the panel, the engine, the metal used for cars, they are weighty. Why? So that air will not be able to blow it off the road. That is why you see most cars, they always talk about the weight. I guess, even don't forget that I've said it, that air resistance too. Air resistance too. So let's go to this experiment, to page 47. Experiment have thoroughly verified that any change in velocity, if there's a change in velocity now, or in that case speed or direction, must be caused by an external force. So if there will be a change in velocity, the only thing that can cause a change in velocity is external force. It's the only external force that can actually cause a change in velocity. Now let's go to the next point again. The properties of a body to remain at rest or to remain in motion with a constant velocity is called inertia. So another name that we can call the equation of first law of motion is what is inertia, because it's talking about objects to remain at rest or to remain in motion with a constant velocity. That's why I call it law of inertia. Law of inertia. Law of inertia. Please don't forget, law of inertia means that it's either is at rest or it's continually moving when the velocity is constant. But some objects have more inertia than the others. Why? That is where the issue of mass comes in. Don't forget that here I mentioned that friction is dependent on weight. So that means that some objects have more inertia than the others. Yes, because of their mass. And don't forget that weight has to do with mass. That was the reason why that I was not using weight as I was using the mass, that a boy of 50 kg and a boy of 5 kg. That is what it's talking about, the mass, which is in kg. So the objects, some objects will have more inertia than the other because of the mass. So let's go to the second one. The inertia of an object is measured by its mass. So what is mass now? Mass is the amount of matter in something. The amount of matter in something is called mass. So if I said I am 50 kg, it means that the total amount of solid, the total amount of gas, the total amount of liquid inside of me is what? Is 50 kg. That's why I call it amount of matter. And when we're talking about matter, we're talking about the state of matter, that is liquid, gas, and solid. So the total amount, the summation of everything is what we bring in the mass. Let's take a look at the next one again. The amount of matter in an object is determined by the number of atoms and molecules of various types it contains. Please pay attention to this. What are those things that can determine the gas, liquid, and solid? They are the atoms. Atoms will form together, atoms, molecules, they form together to give us what we know as solid, liquid, and gas. They will give us what it is. The summation of atoms and then the molecules will give us that. Now, unlike weight, mass does not vanish with location, does not vary with location. The mass of an object is the same on Earth in orbit or on the surface of the moon. So, unlike weight, mass is the same throughout, but weight will not be the same. What is the difference between mass and weight? Is because this one here, for us to get the weight, it has to do with acceleration to gravity. We need to multiply acceleration to the mass to give us the weight. But mass is without acceleration. Meanwhile, weight is dependent on acceleration, and acceleration varies every week. The acceleration on the surface of the Earth is different from the acceleration on the surface of the moon. So the acceleration is quite different. That is why weight is not the same thing as mass. Mass is everywhere. Anywhere you measure mass, anywhere you measure it, you see the same mass. But weight is not the same thing because weight has to do with acceleration to gravity. So let's take a look at this tutorial question now. What is the name given to the axiom of Mechanism that says every particle persists in a state of rest or of uniform motion in a straight line, that is with constant velocity unless acted upon by a force? What is that name? The name is called inertia. Remark on the counter-entities of first law of motion. Now, we're talking about the entities of motion, that there's a counter to it. That does not mean the object will continue moving or the object will remain at rest if there is a constant velocity. And we've said that the only thing is that friction will affect it. Friction affects first law of motion because friction will work against the motion. So let's go to Newton's second law of motion. This law mathematically states that cause and effect relationship between force and changes in motion. This law is used extensively to calculate what happens in a situation involving a force. What will happen if there's a force? Because we know that force is what? Force is something that we can calculate. That is a beauty of mathematics. We use mathematics to calculate anything, provided it's well posed. So, what am I trying to say now is that the law can be written as a single equation, given the exact relationship of force, mass, and acceleration. So, what do we mean by change in motion? A change in motion is equivalent to a change in velocity. What do we mean by a change in motion? A change in motion is equivalent to a change in velocity. A change in velocity means that there is an acceleration. So look at that argument. A change in motion is equivalent to a change in velocity. Because we can say that the motion is changing if there's a change in velocity. And if there's a change in velocity, then it means that acceleration too is there. There's an acceleration. Don't forget that the opposite of acceleration, the negative opposite of acceleration is acceleration. So now let's go again. Connection between the first and second law. Is there any connection between the first and second law? This first law says that a net external force causes a change in motion. Thus, we can see that a net external force causes acceleration. Now, a question for Newton's second law. This is the relationship between acceleration and the net external force. So we can say that acceleration is proportional to what? To the net force. That's the summation of all the forces. Now, meanwhile, the larger the mass, look at it, the higher the mass, then the smaller the acceleration produced by acceleration given force. This implies that the acceleration is proportional to 1 over what? 1 over mass. So, in fact, experiments have shown that acceleration is exactly inversely proportional to mass, just as it is exactly linearly proportional to the net external force. So, you can understand that acceleration is directly proportional to external force, while acceleration is proportional to what? 1 over what? 1 over mass. So, if you mark the two together, this and this, you now see that acceleration is simply of force over mass. So, if you make force the subject of formula, you now see that force is what? Mass times acceleration. So, remark. Let's consider the two again, kinematics and dynamics. Kinematics, method for describing motion without reference to the causes. Here, under kinematics, we are not talking about the force. We are not talking about what is happening to the force. So we're only trying to describe the motion. Without reference, please take note of this. In kinematics, we are not talking about the force. But in dynamics, we really need to emphasize on the force. So here now, nothing like the causes of the motion. But under dynamics, we have force, we have mass, we have acceleration. So should in case you see any question that has to do with How do we differentiate kinematics from dynamics? One, without force, without reference to the force, while the second one has mass, force, mass, and acceleration. Now, let's talk about what is force. Force can be defined as a measure of push or pull on an object. Now, characteristics of force. Force, it has a magnitude and it has a direction. So that is why force is a vector quantity. Now, what about contact force? A force resulting from a direct contact with another object. In the case of contact force, now there is a contact. We know the object that is exerting it, and there's a contact between the two of them. And don't forget, this one will lead us to another third law, which says that at the time you exert a force on an object, then there's a contact, there's an opposite force to it. As I said, action and reaction, they are equal, but they are opposite to one another. So if you have 5 Newton that is pushing an object, then the object is actually exerting 5 Newton force, a force of 5 Newton backward. Now let's consider what's an example of contact force. When you push or pull an object, you exert a force on it. And recall that force pushes or pulls teeth in a particular direction. If you have your teeth now, let's look at it, your teeth. Now you have upper teeth and you have lower teeth. If you exert a force on car, you see that both of them, they will push each other back. So let's talk about another one again. Non-contact force. Even before we go to non-contact force, let's talk about this contact force again. The example is if you are pushing a car. If you are pushing a car, let's say a car is faulty and you want to push it now. No, there's no way, you have to exert a force on it. And that is the same thing that the engine is doing. The engine produces force to move the car against friction. So, non-contact force. You don't have to be standing on the surface of the earth to experience the effect of gravity. As I'm teaching you now, I could feel the effect of gravity on me. Let's get that now. And that does not mean I need to stay, it's not a must. I get it now. But you can feel it that the force is there. So if I can experience that force, and it means that and there's no contact, so we call that one non-contact force. An example is gravitational. Even magnets, if you've seen magnet before, you turn the back of both of the magnets together, you see now that two magnets, they may not touch each other, and there is a way they experience, they exert a kind of force on one another. That's what refers to as non-contact force. So now let's come back here. So the force is what? Mass times acceleration, and is used to define the unit of force in terms of the 3 basic Newton units, which are what? Mass, length, and time. Newton's second law of motion is more than a definition. It is a relationship between acceleration, force, and what? And mass. Like I've explained before, dynamics. Okay, don't let me go there. Then what is the unit of Newton? That is a Newton. That is Newton same thing as what? Kg. What is kg? Mass. What is meter per second squared? That is what? Acceleration. So you can answer that mass times acceleration. It gives us the unit of what? Of Newton. That is the unit of force. And mass is measure of what? Okay, so you can see from here. So how much matter an object contains? I think I've talked about this, and the matter is made up of what? Of atoms and molecules. So how difficult it is to move? So that is how we can use to measure mass. Okay. We measure mass by trying to calculate the total amount of atom inside of it, and we can also measure it based on how difficult it is to move. Like the case I cited the other time, that a boy of 5 kg and a man of 5 kg and a boy of 5 kg, 50 kg versus 5 kg. Notice that they have different amount of mass. So let's go to weight. Weight, however, is the force exerted by gravity on a body. Thus, a heavy truck is difficult to push because of its mass, and it's difficult to lift due to its weight. So that leads us to what we call weight and the gravitational force. When an object is dropped, it accelerates towards the center of Earth. Newton's second law states that a net force on an object is responsible for its acceleration. If air resistance is negligible, then the net force on a falling object is the gravitational force, commonly called its weight. So here we can see that weight is the same thing as force, but here weight, instead of force, it has to do with mass and acceleration, but weight, that is mass times gravity. It has to do with gravity. So in the case of weight, acceleration to gravity is replaced with gravity. So the next thing now is that we quickly take a look at momentum now. because there's no way we talk about force and we won't mention momentum. So what is it? Momentum is just talking about mass times. So if you look at this now, we have force is what? Mass times acceleration. Okay, and if mass should come outside, d dt come here. We are talking about mass times v dt. And what is the v dt? The v dt is what? Is acceleration. So mass times v dt is same thing as well as force. And what is mv? Mass times v here is talking about the momentum. So you can answer that force is the same thing as the p dt. So force is almost the same thing as the rate of change in momentum per time. So that is it. So now that's not all. Here I'm talking about, let's consider the second case again. What if the mass is a constant? Okay, so in that case, you can see that if mass is not dependent on time, then we have force mass times the v dt, which is mass times acceleration, where a is acceleration of the particle. Now, conservation of momentum. If we let f to be 0 in Newton's second law of motion, then we shall have, that is if f is 0 here. Now look at this now. Here, if f is 0 now, we have 0 because d dt of m of v. So in that case, you can see now that if you integrate both sides, you have your m here, then you integrate 0 dt, then you have a constant. That leads us to a theorem now. The theorem says that if the net external force acting on a particle is 0, then its momentum will remain unchanged, which is what we can see here. The momentum will remain unchanged. What then will remain unchanged? That it will become constant. It will be the same thing throughout. Now let's take a look at this example now. Due to a force field, a particle of mass 5 units, or perhaps let's say 5 kg, moves along a space curve whose position vector is given as function of time t. Now look at this, the position vector now. Then we have to find the velocity, momentum, and acceleration, the force field at any time t. So what do we need to do now? Let's start the problem. We know that of velocity that will differentiate the position with respect to time. So if you differentiate, you have this. So what about the momentum? Momentum is what? Mass times velocity. So the mass, then we have the velocity. So you multiply each component, 5 times 6, 5 times 1. Here, 5 will also come and multiply 12, 5 times minus 2 again, then 5 times 4, then we have this. So the momentum of the particle is this. Now what about the acceleration? Acceleration is a change in velocity per time, which is something as second derivative of the position. So if we differentiate this again, are we together? Differentiate? Don't forget how to differentiate. I think you know how to do that. So if you have this, see from here, 2 times 6 will give me 12. So what about force? Force is the same thing as the rate of change in momentum per time, and the force is m times acceleration. So in that case, you have the acceleration, you can multiply this one by what? By the mass. So this is the force pushing the object. This is the force. So that's why we talk about momentum. I won't talk about impulse, which the next lecturer will still explain to you. This next lecturer will explain to you more about impulse, but in my own case here, let me just quickly explain that impulse is when you integrate force within the two times. This is the initial time, this is the final time. Then the rate of change, so the integral of force with respect to time gives us the impulse. So there's a theorem. The impulse is equal to the change in momentum. If you integrate f, the t from t1 to t2, you may notice that this one will give me mv2 minus mv1, that is p2 minus p1, and that is impulse. So the theorem above is true even when the mass is variable, and the force is not conservative. Now let's talk about torque and angular momentum. If a particle with position vector r moves in a force field F, then we define the torque to be r, then curl of F. Then the magnitude of this, which is the torque, is a measure of the turning effect produced on the particle by the force. Now note that if we have this to be r position times force, then it's still the same thing as ddt of mass times r times v. Then this quantity now is what we refer to as the angular momentum. Now let's take a look at this summary. A torque acting on a particle equals to the time rate of change in its angular momentum. So we have the expression of rate of change. So conservation of angular momentum, to note that here we have this to be the rate of change. So It's as simple as that. So, but let's consider this example. We have a particle of mass m moves in xy plane so that its position vector is this. Where a, b, omega are positive constant, a and b show that the force acting on the particle is always directed towards the origin. So how do we solve this now? We know that force is mass as acceleration. Here, that means that we have mass. So we need to differentiate the position vector twice. So if we do that, you have this expression. Differentiate this one twice, you have this expression. So by the time you multiply by m now, you see that m will come inside. So we can factorize this one to come out. Factorize omega squared minus omega squared to come outside. That's why you have minus mass times omega squared to give us. So you answer this one here is still the same thing as position vector. So we now have m omega squared r. What does it mean? This one shows that the force is always directed towards the origin. Towards the origin. So let's consider another example again. Here we have a particle of mass 2 kg moved in a force field depending on time t given by this expression. This is the force. Assuming that when t at t equals to 0, the particle is located at this. That's the velocity of this. Then we have to find the velocity of the position at any time. Now, if you look at this example, you notice that we are giving force now. And from the force, we are asked to calculate the velocity. From the force, we are asked to calculate the position. You know, let's solve it now. And in the second law of motion, you know that force equals what? ma. Now, how do we get the mass? The mass is 2 kg. Now, what about the acceleration? Acceleration is dv dt. So this one is the same thing as ma now. And this is the force that we are giving. You know, we are giving the force to be this. So we are giving the force, then we know that 2 times acceleration will give us. So what's the next thing now is that I can divide both sides by 2. So if I divide by 2, we go here. I divide this one by 2, I divide this one by 2, I divide this one by 2. So we have dv dt. Then we have this expression. Now integrate with respect to t now. The next thing is for us to integrate. If you integrate dv dt, then you have v. Then if you integrate this, we have 4t cubed I. Then if you integrate this one again, you have this. If you integrate this one, you have this. Then the constant of integration is what is c1. Now, since v equals to v naught, and we have this at t equals 0, then we have. Don't forget that we are given this that when t is 0, this is the velocity. Put together. So we need this to find the constant of integration. We need this to find the constant of integration. So at t equals 0, we have this. So we have 6i plus 15j minus 8k. So the first 0, then you put t to 0. We have it. Then what is the next thing? Then we find our c1. So how do we find our c1? Do this. This 0 will go. Then 0, 0, j, then 0, then we have c1. c1 is 6i plus 15j minus 8k, which is this. Hence, we have our b to be this. So this is b, then this is c1. Then b is this. So we have 43, then plus 6, right? We have 90 squared, 80, then plus 15j. Join this and this, and join this and this together. So since v equals to dr dt, we have dr equals to this dt. We integrate again. We need to integrate so that we can have our position. And we have our r naught equals to 3i minus j plus 4k at equals to 0. And what is the next thing is that we set t to 0 here. Why you see t here? Don't forget that this c2 is the constant of integration. So by the time you set the t to be 0 here, so if you equate to this r naught, then with that you can find our c2. Solve a problem like this in class, remember. So this is our position vector. So we join it together, I and j and t, k, I component, j component, and k component. So a constant force F acting on a particle of mass m changes the velocity from v1 to v2 times t. We are asked to prove that F equals to mv2 minus v1 over t. And at the same time, does the result in A above O if the force is varied? We are asked to explain. So here now we have a constant force F acting on the particle of mass m, changes the velocity from v1 to v2 times t. So solution. By Newton's second law, we have our m to be dv dt equals to F. So if we divide here from here, we have dv dt, then we have F over m. This is it. And if F and m are constant, then we have, upon integrating, integrate, we have our V, then we have F over MT, then plus C1. Then using the condition that at T equals to 0, V equals to V1. So we have V1, we have F over M, then when T is 0, then plus C1. So from this, we're only using this condition to find the constant of integration. To find the constant A, which is C1, the constant of integration. So you see that from the C1 equals to what? V1. So from here, we have our V equals to what? F over M, then T plus V1. Using second condition on 3, at T equals to tau, V equals to V2. So we proceed again. We set our V here to V2, then we have F over MT, and T is tau now. We have our V1. So from here, see that V2 minus V1 is what F of V. Just move this one to this side. So the F over M and 5 over tau. So we have this equals to 4. Now, the answer is no, because the result in equation 4 does not hold in general if F is not a constant. Since in such a case, we would not obtain the result of integration achieved in equation 4. Look at what I'm trying to say is that if M is not a constant, here we're able to integrate this one because M and V, they are constants. Because F is a force that we are given, we know that. And if M is not a constant, are you getting that? Then we'll find it difficult to evaluate this kind of integral. That's why I'm saying here that F is not this does not hold in general if F is not a constant, since in such a case we will not obtain the result of integration achieved in equation 4. And if you're unable to integrate this, you know that you'll not be able to achieve this. So let's go to the next example now. A particle is acted upon by the force of this. This is force 1, force 2, force 3. Then we ask to find the force needed to keep the particle in equilibrium. Now, if you look at this now, we are interested to find the amount of force that will make the particle to be equilibrium. And it's very simple. Remember the Newton's third law of motion. We say that action and reaction are what? Equal and opposite. We're going to use the concept here. But mind you, note that we are talking about force. But let's also count the resultant force now. We have 3 forces now. Force 1, force 2, force 3. Let's get the resultant. Now that will give me F1, F2 plus F3. We add the 2 together. Now. So that means that 5 plus 10 plus 15. That will give me 30. So then the force needed to keep the particle is equilibrium is what? Is minus R. So in that case, we have minus of this everything here. With minus. So that means that action and reaction, they are equal and what? An opposite. So the opposite of the force will give us this. So Newton's third law of motion. Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite direction. What this law is saying is that when we have two forces, when we have a force that is acted upon by another force, the first force too will also exert a force back to the other. And that was actually what we actually used to solve this problem, if you agree with me. That's what we use. So now let's remark on this. The force always occurs in pairs, and one body cannot exert a force on another without experiencing a force itself. That is the same thing, even this law is even applicable in real life, that don't attack another person. Because if you attack another person, it may take time, but the person too will attack you back most times. That is why it's better not to just attack. So this law is often termed action-reaction, where the force exerted is the action and the force experienced as a consequence is the reaction. So Newton's third law has practical use in analyzing the origin of forces. So this is the end of the third part. So from Monday now, another person will be around to work with you. But at this point, I would like to say thank you for listening here. I appreciate that. Thank you very much. So wishing you guys all the best. So try to pay attention to this. So if you want to download the PDF, you can check the comment section, the description section. You see the link that you can click where you can download the PDF. So wishing you guys all the best. Thank you very much. Bye bye.
We share
facts within the scope of applied mathematics.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others. Please subscribe to our channel if you like our videos.